Okay, so here we've got number 5 from the work and energy practice. Again, the packet at the end, the problems at the end of the packet. It tells us an 80 kilogram bungee jumper jumps, assuming an initial velocity of 0 meters per second, off a bridge that is 100 meters high, using a bungee cord that is 40 meters long. In order to stay safe, the bungee jumper does not want to get closer than 5 meters from the water below. What is the minimum spring constant for the cord that will keep the jumper safe? And we're going to ignore air resistance. So the main thing we really need to be careful with in this problem is the setup, and what I mean by that is the diagram. I'm going to draw the diagram big on the next slide just so that we can really make sure that we're labeling everything correctly and that it makes sense. And then hopefully once the diagram is drawn, this problem will become a lot easier. Let's assume this is whatever they're jumping from. And then they're going to take the little dive. The bungee cord is going to outstretch. And then it's going to actually extend. So what I mean by outstretch, it's going to go to its length before it actually starts stretching and being elastic. And we're going to call this A, B, and C. I think he goes to water below, so that's down here. He wants to come within 5 meters of the water below. So this distance right here is 5 meters. He starts 100 meters above the water. So there's that distance. And it tells us that the cord is 40 meters long. So the length of this cord right here, not stretched, is 40 meters, which means that the distance from here to the water would be 60 meters. How do I know that? Because the distance from the top to the water is 100 meters. If the cord is 40 meters long, then 100 minus 40 leaves 60 meters to the water when he's here. And then at the bottom, he's going to be 5 meters from the water. So this is what the diagram looks like. And then just to show too, if we're going from here, 40 meters, to right down here, 5 meters above, this is a distance of 55 meters. So 60 meters minus this 5 meters where the water actually is 55 meters right here. So what this 55 meters refers to is how much the bungee cord stretches. So starting from here where it's not stretched at all to here, it's stretching a total of 55 meters. So that 55 meters would be the delta X at, C, not B. So that's how much this spring, it's not a spring, but the bungee cord has stretched. And we have an A, a B, and a C, so the subscripts are important. We know that the mass is 80 kilograms. Tells us that his initial velocity, so his velocity at A, is 0 meters per second, that his height at A is 100 meters. The length of the bungee cord, I'm going to call that L, is 40 meters. It tells us he doesn't want to get closer than 5 meters from the water below, but let's look at from what we did in our diagram. So we know that the height at B is 60 meters, and the height at C is equal to 5 meters. I don't know why I just wrote 55 meters. The height at C is equal to 5 meters, and that's all straight from the diagram. We also know that the bungee cord stretches. So delta X at C is 55 meters, and I did explain that with the diagram. So we are given a bunch of information. Given all of that, what do we want to find? K, spring constant. So let's draw the bar charts. Let me draw these over here. So we'll look at A, B, and C. So A, E, L, E, K, E, G, E, E, L, E, K, E, G, and E, E, L, E, K, E, G. Okay, so at A, there's no spring being stretched or compressed, not moving, is above the base level. It's all EG. At B, the spring where the bungee cord is still not stretched, but he is moving and he is above the base level. And that's not even, let's add a little bit more EG. And then at C, we can assume he comes to rest. He's still above the base level and the spring is now stretched out. So my energy at A equals my energy at B, which equals my energy at C. There's no work being done here. EGA equals EKB plus EGB equals EELC plus EGC. I don't know the speed at B, and it's actually irrelevant since all I'm looking for is spring constant. So I can solve this problem by just setting my energy at A equal to my energy at C. So I'll still break all of these apart into their equations, but we're only going to end up using A and C. So mg height at A equals 1/2 mvb squared plus mg height at B, which equals 1/2 k delta x at C squared plus, I'm out of room, mg height at C. So setting A equal to C, again, because I don't have the speed at B, so there's not enough information to use B, but I could find it if I needed it. We're going to say that mg height at A equals 1/2 k delta x at C squared plus mg height at C. We're looking for k, so let's isolate to solve for that. First thing I'm going to do is get rid of the fraction. So 2mg height at A equals k delta x at C squared plus 2mg height at C. Getting k by itself on the right hand side, 2mg height at A minus 2mg height at C over delta x at C squared equals k. The 2mg is the same, so factoring that out, 2mg height A minus height C over delta x at C squared equals k. So 2 times the mass, 80 kilograms, times 9.8 newtons per kilogram, times my height at A, 100 meters, minus height at B, height at C, 5 meters, over my delta x, 55 meters squared, equals k. So this comes out to 49.24, keeps on going, newtons per meter, 2 sig figs. So k is approximately 49 newtons per meter. Again, the hardest thing about this problem was the setup, and really you had to draw the diagram to really understand what was happening. Determining that the stretch, so delta x at C was 55 meters, came pretty easily once we saw the picture. And again, just making sure that you set everything up, label your A, your B, and your C, and then this became a pretty simple conservation of energy problem.